Good morning, dear students. So today we are going to take up chemical bonding and molecular structure. Very important first year PUC topic. You will get around two questions from this chapter alone. Okay, but it's a very big chapter. Okay, some of the big chapters will be bonding, some basic concepts of chemistry, and basic principles and techniques of organic chemistry first chapter. So these are all equilibrium, thermodynamics, very big chapters, hydrocarbons. So this is one chapter which can fetch you 2 marks overall from first year itself. So here we are going to study different bonds, ionic bond, covalent bond, coordinate bond briefly because there is entire coordination compounds chapter itself in the second PUC. So coordinate bond little bit and hydrogen bond. And metallic bond has been briefly studied in solid state. So of all the bonds, where covalent bond is having more volume of syllabus, that only makes around 70% of the syllabus. So in the rest of the cases, how a bond is formed, some of the examples and factors favoring characteristics, these things we'll study. Under covalent bond, you have theories, Coastal-Lewis theories, okay, and then you have valence bond theory, valence shell electron pair repulsion theory, molecular orbital theory. So all important theories are there under covalent bond. So this is one of the important chapter. We'll take up simultaneously questions and concepts in detail. Okay. So as of now, there is no idea of about postponement. Looking at the success of SSLC examination, there is a question here in the chat. I don't think CET can be postponed. Okay. So because they are firm on that. It should have come by now. Right. Let's see. We'll take up questions now. Okay. Question number 1. When two ice cubes are pressed over each other, they unite to form one piece. Which of the following is responsible to hold them together? Which of the following is responsible for holding them together? Okay. Looking at the options, option D. Exactly. So hydrogen bonds are there expected between two water molecules. So therefore, the hydrogen bonding holds them together, the ice cubes and all. So it is hydrogen. Because between two molecules, there can be intermolecular hydrogen bonds possible. We'll take it next. Most favorable conditions for ionic bond formation. Most favorable condition for ionic bond formation. If an ionic bond has to be formed, metal atom should donate electron easily and non-metallic part should accept electron easily, and there should be large cation and small anion, because to donate electron, cation should be larger. So therefore, what is the answer? High charge small cation doesn't work. Low charge large cation small anion. Low charge large cation large anion. High charge small cation large. So relatively the option B is correct of all the options. Cation should be large, small anion should be small. If charge is more also, it can favor, but the option doesn't go with. We'll take up third. Which of the following has highest lattice energy? See, this lattice energy depends on size of the ions and charge on the ions. size of the ions, smaller the size, higher is the lattice energy, and higher the charge on the ions, higher is the lattice energy. So third question, you can see here, among all lithium plus F minus, Mg2 plus F minus, calcium 2 plus and Ca2 minus, whereas aluminum nitrate, relatively they are smaller ions and also the charge is 3 plus and 3 minus. So with that high lattice energy, it's the amount of energy released when 1 mole of an ionic crystal is formed from its gaseous ions. So that is lattice energy. Higher the lattice energy, highest will be the, or higher will be the ease of formation of ionic compound. We'll take fourth one. Highest covalent character is found in. This covalent character in ionic bond. Covalent character in ionic bond is the concept. There is a rule called Fajan's rule, right? So let me check the options. Shivang says, can you speak little louder? Huh? Am I not audible to others? I'll try to speak, Mr. Shivang. Okay. That's fine. Thank you. Thank you. Anyhow, I'll try to speak little louder. Now, the highest covalent character is found in. Thank you. Okay. We'll proceed. See, what is this? This is the concept based on Fajan's rule. Fajan's rule. So what does Fajan's rule say? See, ionic bond is formed by donating a pair of electron, donating an electron from one atom to the other. The one which donates becomes cation, the one which accepts becomes anion, and they will be held by electrostatic force of attraction, that is ionic bond. After transferring electrons, what would happen? Due to electron withdrawing nature or electron pulling nature of cation, and due to electron donating nature of anion, a kind of covalency will be introduced into the ionic bond. For example, here cation is common, calcium. The anion is fluorine, chlorine, bromine, iodine. Large anion is I. Why have I taken I minus? I'll tell you. So I is larger. So larger ions will have low effective nuclear charge. Calcium being common. So this is large ion can donate electron density towards the cation. The cation will withdraw electron density. Therefore, what would happen? The electron density get distorted. Okay. So the ability of cation to attract the electron density towards itself is called polarizing power. And the extent to which the anion undergoes distortion of electron density is polarizability. So if cation attracts, it is polarizing power. If anion get distorted, it is polarizability. So cation attracts, since it is a large anion, the electron density will be partly shifted towards the calcium like this. So this becomes. Now, when electron density is shifted towards the cation, it becomes a kind of sharing. So sharing introduces covalency. So an ionic compound with small cation and large anion will have higher covalency. Covalency, that is sharing in ionic bond. So if you see, the answer is option B. Fine. Now come on, fifth one we'll take it. The formal charges on the nitrogen atoms from left to right in the azide ion. Azide is N3 minus. This is azide. We generally have this N3 minus. This is nitride. That one. I'll give you the formula if you have forgotten. Formal charge of an atom in a molecule. Valence electron minus lone pair of electron minus half of shared electrons in the bonds. Take 30 seconds and let me. Anybody else got? So you are all giving option B, right? Very good. Okay. See, first the azide ion will have the structure. Okay. So whole negative charge. Okay. This is based on Lewis structure. Count the number of electrons, total number of electrons there, and distribute among themselves. Okay. So if you take nitrogen 7, 1s2, 2s2, 2p3 is the electronic configuration. Now valence electrons in each nitrogen atom will be 5. So 5 into 3, 15 valence electrons plus 1 negative charge, 16 electrons. So 16 valence electron must be distributed so that the octet will be complete here, by the way. So here 2 bonds means 2, 1 bond means 2 electron, 2 bond means 4 electron. So 4 plus 4, totally 8. 8 plus 4 will be 12 plus 4, 16 electron means 8 pairs are distributed. So that octet is complete everywhere. 2, 4, 6, 8. So you can take. So this is finding out the valence electron and writing Lewis structure. After that, let's say this is first atom, second atom, third atom. Let's calculate formal charge of first nitrogen atom. The valence electrons of nitrogen is 5. Lone pair on first nitrogen will be 2 lone pairs are there. Lone pair electrons you have to take 4. Half of, what are the shared electrons? Totally 4. Half of 4. So that's equal to 5 minus 4 minus 2. So it becomes minus 1. So on first nitrogen, it is formal charge is minus 1. Go to N2. So formal charge is equal to, you can take valence electron 5 minus this lone pair of electron at the middle nitrogen atom second 0. Totally half of 8 shared electron in the bonds. 4 bonds means 8 electrons. So it will be 5 minus 4 will be plus 1. Okay. So N3 third nitrogen atom formal charge 5 valence electrons minus same as first one. No, it should be 4 lone pair electrons, and will be half of 4. So to be minus. So you can see this first one will be minus 1, second one will be plus 1. So balance is the plus 1 and minus 1 charge gets balanced. Then where does this negative charge comes from? One of the nitrogen atom negative charge is not balanced. Okay. So minus plus minus 1. So option B is correct, as most of you have given correct answer. Very good. Okay, it's done. We'll take up sixth one. What is the correct order of decreasing bond angle? What is the correct order of decreasing bond angle? Option A. Good, good. Now this ammonium has this tetrahedral structure. Ammonia has pyramidal structure. And one H is removed, in the place of which there is one lone pair extra. So obviously NH2 minus 2 hydrogen and 2 lone pair, like this minus. So this is overall plus. So this is more or less in the order of bond angle of TD. So approximately 109 degree, 28 minutes approximately. This we know because of lone pair bond angle decreases. So it is 107 degree. Obviously 2 lone pair, 2 bond pair is similar to the water. It is approximately 104.5. So if you look at that, decreasing order 105 to 107 to 104. Option A is there. Okay, we'll take up next question. 7th. Among the following, the molecules having same number of lone pair on xenon are. Xenon in uncombined state will have how many electrons? It is noble gas. Octet will be complete. So 7D you say. Very good. Okay. Now in XeO3, there are 3 oxygen bound. Each oxygen takes 2 electrons due to 2 bonds. So 1 lone pair is left. Now in xenon oxyfluoride, XeO F4 complex. Okay. Xenon is bound to 1 oxygen, 2 bonds, means 2 electrons it will take out, and 4 fluorine. Each fluorine take out 1 electron. So 4 fluorine, 4 electrons for bonding, and 1 oxygen, 2 electron. So totally 4 plus 2, 6 electrons have been taken. Out of 8, 2 electrons remain lone pair. Okay. Now XeF6 again. XeF6 has 6 electrons taken away by fluorine for forming covalent bond. 1 out of 8 is still remaining. Okay. This is actually the structure is not required here. Just for your reference, I'm writing. So this is each fluorine and one bond. This bond will be little bent because of lone pair. Okay, not to worry. So this is the answer. So molecules having same lone pair of electron, so they all have one lone pair electron each. Therefore, option D is correct. Shall we proceed now? We'll take up 8th question. The correct order of increasing bond length of CH, CO, CC, single bond, CC, double bond. Exactly. Here, size of the atom, hybridization, electronegativity, everything counts. Is it okay? So double bond 134 around, single bond is 154 picometer around, and CH hydrogen is smallest. So CH bond is smaller or lesser than C double bond C, and between carbon single bond, carbon oxygen single bond, oxygen is more electronegative. So higher the electronegativity of the bonded atoms, lesser is the bond length. So in that way, option B is correct. This is small because of double bond. Oxygen electronegative, and highest is CC bond. Okay, we'll take up further. 9th question. The decreasing order of dipole moment of the molecule. See, as bond angle decreases, dipole moment mu increases always. That's one of the important aspects that affects dipole moment. You can see water has bent structure. So 104.5. Whereas ammonia, pyramidal. This is 107. And between ammonia and NF3, because of electronegativity of fluorine, the dipole moment decreases. Then boron trifluoride actually a symmetric molecule, trigonal planar geometry. Rather, mu will be 0 here. So bond angle is least. So dipole moments adds on, and then 107. Okay. Then NF3. Between NF3 and NH3, NH3 has more dipole moment because to some extent this fluorine atom balances the electronegativity. Here nitrogen acts like this and fluorine acts like this. Whereas in case of ammonia, bond moments add up. So therefore, overall order will be option C. In BF3, it get cancelled, equal and opposite forces. Okay, like this. We'll take 10th one. Megha says C. Zainab, C. 10th is, in which of the following pairs both molecules possess dipole moment? The carbon dioxide, so it is linear and bond moments therefore get cancelled. Okay, so they are asking both the molecules are have dipole moment. BCl3 is similar to BF3. It is mu0. Okay, here carbon dioxide is mu0. In case of water, both are bent molecules in option C. Okay, so both are 16th group elements. So obviously bent means dipole moment doesn't cancel. Here this will be 0. So which is correct answer? Option C. Good. Next we will take up 11th one. Which of the following would have a permanent dipole moment? That's already, I told depends on the structure. Which of the following would have permanent dipole moment, not 0? Okay, I'll give the structures. You can decide on. The SiF4 similar to CH4, because silicon is below carbon. Same structure, tetrad. Okay, what is the structure of SF4? Anybody has idea? What is it called? Seesaw. Xe has square planar. Square planar geometry. Can you give me answer now? Net dipole moment. See, symmetric molecules will have 0 dipole moment because bond moments get cancelled. So mu is equal to 0. Tetrahedral is symmetric and square planar symmetric. Bond moment get cancelled. Here it is because of lone pair, and also it is seesaw we say. It is not a symmetric structure. Mu is not equal to 0. So they're asking which has a permanent dipole moment, not 0. So mu is not equal to 0 is option C, SF4, not D. Many of you have given D. Okay. Sure, you can write on that. Okay, we'll proceed to 12 now. Which of the following is a non-polar molecule? Is it 12C is non-polar? Always remember, especially for diatomic molecules. Okay, in case of diatomic molecules, if it is homodiatomic, non-polar, having same atoms in the molecule. If it is heterodiatomic, diatomic, then it is polar always. See, this is heterodiatomic, so polar it is. Water is bent and it is heteropolyatomic. And CHCl3, there is one hydrogen, 3 Cl. If it were to be CCl4, it would have been non-polar. Bond moments doesn't cancel each other, so it is only methane. Prajwal.
ಹೇಳಿ ಸರ್.
ಇದನ್ನ ಪಬ್ಲಿಕ್ ಚಾಟ್ ಇದು ಮಾಡಿ
ತೆಗ್ದಿದೆ ಸರ್.
ಹೋಸ್ಟ್ ಜೊತೆ ಮಾತ್ರ ಕೊಡಿ ನೋಡಿ. ಡಿಸ್ಕಷನ್ ನಡೀತಿರ್ಬೇಕಾದ್ರೆ ಪೀಪಲ್ ವಿಲ್ ಗೆಟ್ ಡಿಸ್ಟ್ರಾಕ್ಟೆಡ್.
ಚೇಂಜ್ ಮಾಡಿದ್ದೀನಿ ಸರ್.
ಓಕೆ, that's fine. We'll take it further. The dipole moment of ammonia, is it higher than NCl3 or smaller than NCl? The NH3, I told you some time back with NF3. Okay, so all bond moments will act towards more electronegative nitrogen, whereas in NCl3, because of this Cl, okay, if this nitrogen acts like this, Cl will reduce that bond moments. So mu will be less here and the mu will be higher. So option. Come on. We'll take up 14. Shape of O2F2 is similar to that of. Shape of O2F2 is similar to that of. Okay, looking at the options. Okay, the O2F2 is similar to hydrogen peroxide. It is non-planar structure. Okay, so which is equivalent to this H2O2. We'll take 15th one. Which has more number of lone pairs on the central atom? Which has more number of lone pairs on the central atom? looking at that, PF3 is similar to NH3 because phosphorus is below nitrogen. XeF6 I wrote sometime back, distorted octahedron. Okay, so Xe will have one lone pair. Okay, SF4 is CISA, so one lone pair again. 6 electrons are there. It is CISA, one lone. What about BRF3? BR will have 7 electrons in the elemental state, or if in uncombined atomic state. So out of 7, 3 are used. So BR will have this shape. Okay, this is called T shape. So answer is option D. (16) in OF2, number of bond pairs and total number of lone pairs of electrons are respective. Bond pairs and lone pairs. It is not O2F2, it is OF2. Can it be 9 electrons? Any answer? So option B, right. Let me write this. Oxygen is the central atom. Fluorine. Now oxygen, out of 6 electrons in the valence shell, 2 of which are used. Remaining 4 electrons is there as 2 lone pairs. Fluorine, out of 7, 1 is used for bonding. 6 electrons remain as 3 lone pair. So it is quite evident 2 bond pairs are there. How many lone pair? Each fluorine 3 plus 3, 6 plus 2, totally 8. Okay. 2 on oxygen, 3 plus 3 plus 2, 2 and 8. Okay. Next we'll take 17th. The electronegativity difference between nitrogen and fluorine is greater than that between nitrogen and hydrogen. Yet dipole moment of ammonia is greater than that of NF3. This is because we have got this kind of examples and explanation also. Exactly as most of you are giving answer. In option D, in ammonia, dipole moment and atomic dipole and bond dipole are in the same direction. All. Whereas in NF3, these are in opposite direction. So that means I wrote some time back also. Okay, so dipole moments will add up here. Those lines. In NF3, dipole moment will be opposite. So that's why bond moment will cancel, and therefore bond dipole moment decreases. So option D is correct. Take 18. The bond order of a molecule is given by. This is based on MOT, bond order, so option C, D, A. So this time there is division. Completely the options are divided now. A, B, C, everything you get. The bond order. What is bond order formula? Okay. I'll give the answer. Bond order is equal to number of bonding electrons minus number of electrons in anti-bonding molecular order divided by 2. Bonding electrons minus anti-bonding electrons by 2. So it should be half the difference between electrons in bonding and anti-bonding. 19. Which of the following is an example of octet molecule? Is octet complete in any of these? Looking at the structure, it's never. Octet is not complete in ClF3, PCl5. Rather, it is expanded octet structure molecules. Option D is correct. When Cl forms one bond, its octet will be complete. Similarly, 5 bond means 5 into 2, 10 electrons are there. It's not complete. 7 into 2, 14 electrons are there. So none of this is correct. 20th. In the octahedral structure, the pair of d orbitals involved in D2sp3. Okay, Shivang says 20, option C. Okay, any answer? See, D2sp3 hybridization requires 2 d orbitals. Of the 5 d orbitals, you can segregate them into 2 categories. Okay, so D 1, 2, 3, 4, 5. See, this is dxy, dyz, dxz, dx square y square, dz square. These 3 are similar, where lobes of d orbitals are there between the axes. These 2 have d orbitals lobes along the axis. Now, how many d orbitals have to be involved in D2sp3? Only 2. So 2 orbitals of one type will be involved in D2sp3. So it should be option C. Okay. We take 21. Four diatomic species are listed below in different sequences. Which of these presents the correct order of their bond orders? No. Afra, when there is hybridization like D2sp3, there should be only 2 orbitals of similar type. If it is instead of D2 sp3, it is D3 sp2. Okay, so where it becomes completely 7 orbital, D3 sp3. Pentagonal bipyramidal, that is the case of IF7. In such cases, 3 orbitals of dxy can be involved, or sp3 d3 we say, right? So always it goes like that. Okay, right. See, looking at the 21, the options B, C. Okay, I have got only one answer for 21, B, Shivank. What I'll do is I'll give a brief explanation about molecular orbital diagram. How do you write? How do you calculate bond order? Probably you would have forgotten. In brief, I'll explain. Pay attention. Okay. I think I'll take a page. Then we shall come back. Okay. See, MO diagram. So based on molecular orbital theory, if two atoms A and B have to combine to form a molecule AB, the atomic orbitals of A, atomic orbitals of B should undergo a process called as LCAO, linear combination of atomic orbitals. LCAO of atomic orbitals of combining atoms leads to molecule which has molecular orbitals. In an atomic orbital, electron reside in the atomic orbital, whereas in molecule, electron reside in molecular orbital. Atomic orbitals are monocentric. There is one nucleus. Molecular orbitals are polycentric. Electrons move under the influence of many nuclei. Fine. If one orbital of A, one atomic orbital of B undergo linear combination, 2 MOs will be obtained. So that means number of atomic orbitals which undergo linear combination will be equal to number of molecular orbitals which are formed. And always there will be 2 types of molecular orbitals: bonding molecular orbital, anti-bonding molecular orbitals. These are less energetic and therefore more stable. These are more energetic and less stable. Okay, so you better remember oxygen molecule formation, which can lead to conclusion of any other species. I'll tell you how. Atomic number of oxygen is 8, means each oxygen has 8 electrons. So in O2 there must be 8 plus 6, 16 electrons possible. Now 8 electrons are there in 1s2, 2s2, 2p4. That means when 2 atoms of oxygen undergo linear combination, 1s, 2s, 2p orbitals of each oxygen should undergo linear combination to form molecular orbital. Let us take up now. So how do you construct molecular orbital diagram? If this is energy axis, okay, this is oxygen atom, this is another oxygen atom. Here is 1s orbital, 1s orbital. They are both undergo linear combination to give 2 MOs. So whatever we write at the center is molecular orbital. Okay, this is for O2. Now, this is 1s2 and this is also 1s2 of 2 oxygen atoms. There are 2 electrons each. Okay, always s orbitals undergo linear combination to form sigma type of molecular, and this is sigma star 1s. Okay, next is, I'll allocate electrons later. 2s and 2s. They undergo linear combination to form sigma 2s and sigma star 2s. like this. Correct? Now again 2s orbitals have 2 electrons each. 2 electrons. Fine. Then it is 2p subshell. There are 3 orbitals. So there are 4 electrons in 2p in oxygen atom. Now the p orbitals, 3 p orbitals of p subshell are mutually perpendicular to each other. Okay, it is, if it is x y z axis like this. So px will be oriented along x axis, py will be along y axis, and pz will be along z axis. So they are mutually perpendicular to each other. So always when 2p and 2p undergo linear combination, by convention we assume always pz orbital to form sigma. We consider it as an internuclear axis. pz to form sigma type. Remaining px and py undergo linear combination with px with px, py with px to form pi bonding, anti-bonding. So pi y, pi x. So totally 3 plus 3, 6 molecular orbitals have to come, of which there will be 2 sigma type. This is sigma 2pz, sigma star 2pz, and remaining px is there, py is there, pz undergo axial overlapping to form sigma. Remaining px and py, they undergo sidewise overlapping to form pi molecular orbitals like this. Just join this. This is symbolic way of representing linear combination. That's all. What is this now? I'll write with a different color. Pi 2px, pi 2py. This is anti-bonding pi, pi star 2px. It will be having same energy as that of pi star 2py. Now, come on, let us arrange the electrons. 1s2, 2s2, 2 plus 2, 4 electrons will go 2 here, will go here, and 2 will go here. Right. Similarly, like this. 2 plus 2, like this. Now, for these MOs, molecular orbitals, Aufbau principle, Pauli's exclusion principle, Hund's rule, everything is applicable. So here 4 plus 4, 8 electrons are there. So first electron will go to lowest energy, this one. Then Hund's rule is applicable here, 1 1 each, and then pair like this. Now 4 plus 4, 8 electron, 2 4 6, remaining 2 will go here singly like this. Pi star 2px, pi star 2py. So this is how electrons. Now better remember, every time you will not be able to write the MO diagram like this. So better remember the increasing energy order of various molecular orbitals always. Okay. If you see increasing order of energy, so that you can calculate bond order, write electronic configuration, all these things. Sigma 1s, okay, has less energy than sigma star 1s, than sigma 2s, sigma star 2s. Then comes sigma 2pz, which has less energy than pi 2px, which has equal energy than pi 2py, less than pi star 2px, equal to pi star 2py, less than sigma star 2pz, so on. So you just remember, no need to write MO diagram at all. Okay. So let's say oxygen molecule has electrons 16. How do you arrange? Each orbital can accommodate 2 electrons. No need to write MO. Just write the sequence. 2 here, 4, 6, 8. Here will be 10. 1, 1, 1, 1. So 2, 2. Correct? No? 12 and 14. 1 here. Okay, like this. Now, how do we calculate bond order? Bond order is equal to NB minus NA. If you count all the bonding electrons, I'll just underline with red bonding electron. 2, 4, 6, 8, 10. Correct now? So 10 electrons, this is by 2 in bonding. How many are anti-bonding? I'll underline with purple. 2, 4, 6 here. So 2p, pi star 2p x1, pi star 2p y. Sigma star 2p is empty. So here 6 divided by 2 will be 4 by 2, 2. So there are 2 bonds. Bond order always indicate number of bonds between them. Now, last 2 electrons are unpaired. Whenever the molecule has unpaired electron, it will be paramagnetic. It will be weakly attracted by external magnetic field. So these things. Now, know this oxygen like this. Rest everything you can decide on. O2 minus. That extra electron, where does it go? You look at the MO diagram. O2 minus has extra electron, right? That has to be added. Where is the extra electron space? Only in pi star 2px. It will go here. If electron in anti-bonding increase, how do you calculate bond order? NB minus Na. So this is 10 minus 6 by 2, right? This electron goes to anti-bonding. So 10 minus 7 by 2 is equal to 3 by 2, 1 point. Still there will be one unpaired electron. It is paramagnetic, like that. O2 2 minus. Bond order. Where does that extra electron go? There was one more space available in pi star 2px. It will go here. So that bond order 10, that electron is added to anti-bonding, it becomes 8 by 2. So that is 2 by 2, 1. So it will be diamagnetic. Similarly, O2 plus. How do you get O2 plus? Remove one electron. From where do you remove electron? Valence shell. There were 2 electrons in the valence shell. It becomes 10 minus 5 by 2 is 2.5. It is still 1 electron is unpaired, paramagnetic. O2 2 plus. Remove 2 electron from oxygen. From where do you remove? Anti-bonding. So 10 minus 6 becomes 4 by 2 is 3. And rest after removing 2 electrons, only paired electrons will be remain. Knowing bond order of some of the other species. Let's say F2. Fluorine, you need to decide on bond order. How many electrons are there in fluorine? 9 plus 9, atomic number, 18. Which species of oxygen has 18? So look at that, O2 2 minus. 16 plus 2 electron extra, 18. What is the bond order? 1. What is the nature, magnetic nature? Dia. So you can easily say bond order 1, it is dia. That's all. Okay, we'll take up CO. How many electrons are there in CO? It's a heterodiatomic molecule. 6 plus 8 is equal to 14. Which species of oxygen has 14? You can see O2 2 plus. So 16 in oxygen minus 2 is equal to 14. Correct? So 14 with that 3 bond order diamagnetic. So this also bond order will be 3 and it will be diamagnetic. One thing you should know, whenever combining atoms have atomic number of the atoms less than 8, then this sequence will slightly change. So sigma 2pz has less energy than pi 2px. No, that will only change. Sequence of energy will slightly change. Pi 2px will have same energy as that of pi 2py. Will be having less energy than sigma 2pz. The sigma 2pz was here, it will be shifted there with only. For example, nitrogen. So this will be same. For example, carbon, because atomic number is 6, 7, nitrogen. B2, like this. How about lithium? Lithium, there is no question because atomic number is 3. There is no electrons in P itself. So this is the advantage of knowing the MO diagram of oxygen. Sigma star. Okay, I'm looking at the question. Shivank, sigma star is anti-bonding. Sigma is bonding. Raj Malhotra, geometry of a compound can be decided based on valence shell electron pair repulsion theory. Point number 1. Second, hybridization of VBT. And if it is linear, some common sense also work out based on the electron pair and everything. So there are many ways. See, this chapter is so huge. In the regular classes, even if you do 12 to 15 session, still there will be kind of unsatisfaction with the teacher. I would have done 2 more sessions then. So 12 to 15 sessions of 1.5 hours, I'm telling. Whereas CET now I have to complete this in 1 hour, one session, 1.5 hours. So somehow you have to be ready with the synapses so that I can only clarify the doubts. Fine. Now I think with this kind of bond order of different species of oxygen, other species also which you have not worked out also can be concluded. Okay, so we'll get back to the questions. Okay, which of these represents the correct order of their bond order? Can anybody? There are some species which I have not discussed there because helium and all. Helium He2 plus is there. 2 plus 1 electron, 3 electrons are there. So bond order will be sigma 1s2 sigma star 1s1. So 2 minus 1 by 2 is half. Okay, likewise. See, you will do one thing. You strike off this carbon. It should be O2 minus, not CO2. Concept of polyatomic MO becomes very complex. It should be diatomic or heterodiatomic. Not there is no carbon actually. Look at the options. That's misprinted. Typo error. O2 2 minus, O2 2 minus is bond order half. Sorry, 1 by 1.5. Half reduces. NO, how many electrons are there? 7 plus 8, 15. 15 is like O2 plus, what was the bond order? 2.5. C2 2 minus, 6 plus 6, 12 plus 2, 14. 14 electrons are there. 14 is bond order similar to O2 2 plus 3. So bond order half, 0.5, 1.5, 2.5 and 3. So option B is correct. Shall we proceed now? We'll take up next. Fine, thank you, thank you. 22. The stability of ionic crystal depends principally on it is lattice energy. So as delta LH increases, stability also increases. Okay. Shall we proceed now? What is the formal charge of carbon in carbon dioxide? Can you calculate? Formal charge of carbon in carbon dioxide. I'll give you structure. You know this also. Calculate formal charge. Done. Third A 0. Shrija. Aisha, option C. Okay, let me give you this formal charge as valence electron minus lone pair minus half of shared electron or bonded pair of electron. For carbon, so 1s2, 2s2, 2p2. 4 valence electron. Is there any lone pair here? No. How many bonds? 4 bonds means 8 electron by 2. So 4 minus 4 is 0. So 0 formal charge. Okay, shall we proceed now? 24. Any one of the three equivalent resonance forms of for the carbonate ion would show around the carbon atom 3 single bonds, 2 single and a double bond. What is that exactly? Option C, 3 single bonds and 1 lone pair. Is it so? Carbonate radical structure. Carbon is there at the middle. There are 2 negative charges. So one oxygen is doubly bound, and remaining oxygen, if they become doubly bound, carbon valency wouldn't satisfy, and negative charges also wouldn't come. So singly bonded oxygen will be negative. So what is the answer? This is CO3 2 minus. Of course, it undergoes resonance. It goes like so. 24, option B. Correct. 2 single and a double bond. Fine. 25 will take. Which of the following has p pi d pi bond? Now the question is, what is this p pi d pi bond? Yeah, na? See, a pi bond is formed by the sidewise overlap of orbitals, atomic orbitals, right? Now, when two p orbital overlap sidewise, it is called p pi bond. If one p orbital and d orbital undergo sidewise overlapping to form a pi bond, p pi d pi. Likewise, it is d pi d pi. Can there be s pi like that? Is that it possible? S pi. It is not possible because it only gives sigma bond. So this is not possible. So only p pi like. Okay, coming back to this question. Which of the following has p pi d pi bonding? See, in order to have P and D undergo sidewise overlapping to form a pi bond. See, nitrogen to oxygen. Nitrogen has only 2 shells. In the second shell, there is no d orbital at all. So there is a possibility of only p pi d pi. So the central atom should have to have d orbital in it. So sulfur is 1, atomic number 16. It can have 3 shells. So it is 1s2, 2s2, 2p6, 3s2, 3p4. Correct, no? So it has d orbital which is there in the third shell empty. That can be involved in sidewise overlapping with surrounding oxygen. So as a result, option B is only possibility with this. You can see again, boron is a second period element, has 2 shells, carbon 2 shells, nitrogen 2 shells. Shall we proceed now? Once again. Fine. We'll take up 26 now. Among the following, the pair in which the two species are not isostructural. What do you mean by isostructural? Having same structure. Okay. Among the following, the pair in which the two species are not isostructural. See, look at this option A. SiF4 is tetrahedral. I had written some time back. SF4 is what? Seesaw. So they're not having same structure. Rest have same structure. One second. I'm just looking at this participants. Some virtual. Okay. Okay, we'll take a further. 27. The state of hybridization of C2, C3, C5, and C6 of the hydrocarbon. Now, what is the concept? In any hydrocarbon, singly bonded carbon atom, sp3 hybridized. A doubly bonded carbon atom, sp2 hybridized. A triply bonded carbon atom will be sp hybridized. One second. Prajwal, can you
ವಾಯ್ಸ್
hear me?
ಕೇಳಿಸ್ತಾ ಇಲ್ಲ ಸರ್.
Hello, Prajwal.
ಸಿಕ್ತು, ನಮ್ಮ ವಾಯ್ಸ್ ಕೇಳಿಸ್ತಾ ಇಲ್ಲ ನಿಮ್ದು.
ಈಗ ಕೇಳಿಸ್ತಾ ಇದೆಯಾ?
ಈಗ ಕೇಳಿಸ್ತಾ ಇದೆ, ಅವೆಲ್ಲ ಕೇಳಿಸ್ತಾ ಇದೆ. ನೀನು ಹೇಳ್ತಿದ್ದಲ್ಲ ಎಕ್ಸ್ಪ್ಲೇಷನ್ ಆಗ್ಲಿಲ್ಲ ಅದಕ್ಕೋಸ್ಕರ.
ಇಲ್ಲ ಬೇರೆಯವರೆಲ್ಲ ರೆಸ್ಪಾಂಡ್ ಮಾಡ್ತಾ ಇದ್ರು, ನಾನು ಮಾತಾಡ್ತಾ ಇರಲಿಲ್ಲ. ಮೋಸ್ಟ್ಲಿ ಯಾವಾಗ ಹೇಳ್ತಿದ್ದೀರಾ ಅನ್ಸುತ್ತೆ.
ಓಕೆ ಸರ್, ಥ್ಯಾಂಕ್ ಯು.
Okay. Now, okay, I was just looking at the option B is right? Option D, option 27D, something like that. Okay. See, C2, which is C2 here, triply bond. So it should be sp hybridized. And C3 is singly bound sp3 hybridized. C5 is doubly bound sp2 hybridized. C6 is singly bound again sp3 hybridized. So what is the correct answer? C2, C3, sp, sp3, sp2, sp3, sp, sp3, and sp2, sp3. So option D is right. We'll take up 28. which of the following order is correct for the dipole moments of dichlorobenzenes? As bond angle decreases, dipole moment increases. Always. That's the thing. And this 2 has 0 dipole moment because equal and opposite dipole moment get cancelled. So you can see angle is very less here in 1, next 3, next 2. Should be option C. Next, 29. How do dipole moment mu and angle theta change with a change in sp3, sp2 to sp? See, sp3 to sp2 to sp. This is, what is the bond angle here? 104, 109 degree, 28 minutes. 120 degree, 180 degree. As bond angle increases, theta, mu decreases. So looking at that, mu decreases as theta increases. Next we'll take 30. Lattice energy of calcium chloride is U and that of sodium chloride is U dash. For same crystal structure and same ionic radii of calcium and sodium, what is correct? Same ionic radii also they have given and same crystal structure. So calcium has 2 positive charge, sodium has 1 positive charge. It's monovalent cation. So obviously calcium chloride lattice energy must be greater than sodium chloride lattice energy U dash. So option B is correct because the lattice energy here they have represented as U directly proportional to magnitude of charge. Next, we'll take up 31. Decrease in S character in hybridization decreases the bond angle. That is one observation. Okay. Sp, 180, Sp2 120, Sp3 109. In water molecule, bond angle is 104.5 degree. The S character in hybridization of oxygen atom in water is likely to be. They have given decrease in S character in hybridization, decrease the bond angle. Okay. So as percentage S character decreases, bond angle decreases. Now, in oxygen, in water, the oxygen is sp3 hybridized. sp3 hybridized. In sp3 hybridization, percentage S character is 100 divided by 4. No, there are 4 orbitals. So 25% percentage S character. Now, if sp3 hybridization takes place, what is expected bond angle? Tetrahedral 109 degree, 28 minutes. But what is the bond angle in water? In water, it is less than tetrahedral bond angle due to lone pair repulsion, 104.5 degree. So, percentage S character in hybridization decreases with bond angle. For 109 degree, 28 minutes, what is expected bond angle? 25 degree. Expected percentage S character, 25%. So, less than that means, therefore, percentage S character should be less than 25%. You can write the answer. Shall we proceed now? 32. Formation of which of the following cannot be explained by using valence bond theory? Valence bond theory explains the formation of molecule due to overlapping of atomic orbitals like this. Okay, that means the combining atomic orbitals containing unpaired electron, when they overlap with the spin of electron opposite, when they overlap, they form a sigma bond, sidewise form pi bond like that. But H2 plus has one electron. N2 plus also has odd electron. Correct? No, actually N2 has 7 plus 7. One electron is removed, means it should be 13 electron. There is an odd electron here. So as a result, both A and B, so they are odd electron species, which was not considered under valence bond theory. Right. 33 will take. The electron probability density, which is given by psi square of bonding molecular orbital, is higher than the sum of individual atoms, individual atomic orbitals, by a factor. Anybody knows this? The bonding molecular orbital is formed by constructive combination. Constructive combination or symmetric addition of wave functions of atomic orbitals of combining atoms. Okay, atomic orbitals of combining atoms. Now, when two atoms A and B combine to give molecule AB, atomic orbitals of A and B should undergo linear combination. Let's say there is an atomic orbital where wave function of electron is psi A, atomic orbital of B where wave function of electron in B is psi B. And if it gives a molecule, it will have electron in the molecular orbital with wave function psi AB. So as I told you, bonding molecular orbital is formed by constructive combination or symmetric addition. So psi AB bonding will be formed by symmetric addition, psi A plus psi B. If you want electron density formed, then you have to square it. Square and square. So A plus B whole square formula. Psi A square, psi B square plus 2 psi A psi B. This square of the wave function gives electron probability of finding. Okay, like this. Now you can see electron density in bonding molecular orbital is just not equal to sum of the electron density of combining atoms A and B, but it is more by a factor 2 psi A psi B. So answer is option C. In case of ABMO, it would become, psi A square, because it becomes psi A minus psi B. Then if you do whole square, psi A square plus psi B square minus 2 psi A psi B. Okay, so it will be less by a factor this, but they are asking bonding molecular orbital, it will be more by a factor 2 psi A psi B. That's why the BMO will be having more electron density between nuclei and it will be more stable than antibonding. Okay. Okay, that is done. We will proceed now. 34. The diagram shown here. See, different molecular orbitals will have different shape and structure, right? So here 34, you can see there is a nodal plane also there in between, and two lobes are there. So it should be head-on overlapping of two p orbital, which has resulted this kind of arrangement. So it should be sigma npz. Different shapes of MOs, those are also important. They'll ask you this. For example, 35th. You can see four lobes are there, which would be formed by the asymmetric combination, okay, or destructive combination of p orbitals. See, if p orbitals they undergo overlapping, like this is plus, minus, plus, minus. This is called destructive combination. It gives the kind of the MO which is having four lobes like that. So it is destructive means pi star, sidewise means pi. So it is like this. It is axial, direct head on. It's not sideways. So sigma. Okay. 36 will take it. The decreasing order of bond length for N2 and its ions is correctly shown in here. N2 has 14 electron, similar to that of O2 2 plus, but with this change in sequence of sigma 2pz, pi 2px, pi 2py. That's all. So in case of N2, 14 electrons are there. I'll write electronic configuration sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. Actually, next sigma 2pz2 should have to come. Since atomic number is less than 8, it is pi 2px2, pi 2py2. Totally 2, 4, 6, 8, 10, 12 electrons are over. Then sigma 2pz2, 14 electrons are over. So all are paired. N2 is diamagnetic, and if you calculate bond order, it becomes 10 minus 4 by 2 is 3. Okay, that's it. Bonding electrons. Okay, 2, 4, 6, 8, 10. Anti-bonding electron 2, 4. That's all. So it's like that. They are asking about the species, different species. I'll write N2 plus. So to remove one electron from bonding only, last is bonding. So bond order becomes 10 minus, sorry, 9 minus 4 by 2 is 2.5. N2 plus, correct? Similarly, N2 plus 2, they have given. Remove 2 electrons of this. Bonding you have to remove. 10 becomes 8 minus 4 by 2 bonding. It is therefore 2. And there is negative also. N2 minus is also there. Let us calculate. Bond order is equal to, you have to add electron. Adding electron would be possible only when that electron go to pi star 2px. So anti-bonding. So it becomes 10 minus 4 becomes 5 by 2. It is 2. You can see N2 minus, it has 15 electrons, similar to that of O2 plus. O2 plus is 2.5, N2 minus is 2.5. Similarly, have they given N2 minus 2? Right. N2 2 minus. How many electrons? 14 plus 2, 16. Is it similar to oxygen? So 2 electron will go here, option. So check the bond order now. Give me the correct option. N2 2 minus, bond order 2. And N2 2 plus, also bond order 2. N2 2 minus, N2 2 minus, N2 minus, I'm telling you. N2 minus has 15 electron, 2.5, right? N2 plus also 2.5, and this is 3. So option B is correct. Okay. So that's fine. In the same way, you can decide on bond order of oxygen. So nodal planes, looking at the geometries and everything. Okay. So remaining around 60 questions are there probably. So you take it as home assignment. Okay. So 58 questions are there.
So time up,
For
sir.
this, we'll meet for the next class with D and F block elements and coordination compounds. Okay. So fine. We'll meet for the next class. Thank you very much. We will send PDF will be sent.